Differential equations, our last day on 7.4, day 3. We're going to deal with the transformation of a periodic function, the transformation of a function that repeats itself with a period of capital T. So let's say f of t is piecewise continuous from 0 to infinity, and it's periodic with a period of t. Unbelievably, you have this very simple formula. So the Laplace transform of f of t would be 1 over 1 minus e to the negative s times the period capital T. That's a constant. We will integrate from 0 to capital T of e to the negative st multiplied to that function. And if you work that integral out, you will have really found your Laplace transform. So let's look right here. Finding this Laplace transform, you can see we have a step function that is in fact periodic. You can see that you start up with a y value of 1 until you get to x equals 1, and then it drops down to 0. It'll be 0 from 1 to 2, but then we'll elevate again, going up to a y value of 1 from 2 to 3. Right after that, we drop down to 3 to 4, and so forth. The way we could describe this, and in fact, we'd like to describe it really for all, x values or t values. We can say, look, we're going to start off with 1 between t values between 0 and 1, not including the 1 itself. But then we drop down to 0 from t greater than or equal to 1 and less than 2. But then this right here is your period. Your period is 2. It will take 2 units to go through this kind of a repetition. And a way to generalize the infinite pattern that continues on, you could just say that f of t plus 2 would equal f of t. That's a wonderful way to represent this continued pattern forevermore. And you could quickly confirm if you were, plugging in a t value of, say, even a 1. If you'd add here, that would be the same thing as f of 3, because 1 plus 2. Well, in any event, once you identify that your period is 2, we can go ahead and we can create and go through this pattern. We can say, let's go ahead and find the Laplace transform of f of t. If you look at the top page here, we'll say this is 1 all over 1 minus e to the negative s times, well, your period is 2. And then we're going to integrate between 0 and 2. Even though this pattern continues forever, we're only going to integrate between 0 and 2. And then we'll have e to the negative s of t multiplied to f of t dt. What am I doing? I'm just copying down what we're seeing in this star pattern at the top of the screen. And at this point, just want to tell you that obviously your function, if you were to look right here, between 0 and 2, there are 2 separate definitions that we're going to have. So, of course, out in front, we could say this is 1 minus e to the negative 2s. But really, this integral can be broken up because the piecewise function here, we've got 2 parts, 2 assignments. We could say, look, we're going to have this e to the negative st times 1. My f of t is 1 right here from 0 to 1. But then what? From 1 to 2, this is very nice. Our f of t is 0. And wonderfully, that second component is just going to completely wipe out. So let's go ahead and see if we can finish this integral up. We'll have 1 minus e to the negative 2s. And as we do an antiderivative here, with respect to t, we're going to have to reverse the chain rule. We'll have e to the negative st. Taking a derivative with respect to t, we'd have to multiply by negative s. Reversing the chain rule says we're going to have to divide by that negative s. and then apply our bounds from 1 to 0. Now, immediately you can see you've got a 1 and a negative s down here, 1 all over negative s. You could quickly combine that together. You can pull that negative 1 over s, and then here we have our 1 minus e to the negative 2s. See, I'm putting little edges here on my s's so I don't mistake them for 5s. Using the fundamental theorem, however, we could say that plugging in a 1, we'd have e to the negative s. Minus, when I plug in a 0, well, e to the 0 is actually just a 1. Well, I could go ahead and distribute this negative 1 to everything up on top, and this minus 1 would become a positive 1, and then I'd have a minus e to the negative s. However, I think if we look very, very closely, you could see that down below this is a difference of squares. This denominator will in fact factor unbelievably. So just finishing this problem up, you can see that because this is a perfect squared term, I'd have 1 plus e to the negative s and 1 minus e to the negative s. And you can see this 1 minus e to the negative s is going to cancel, leaving us with a final answer of 1 over s times 1 plus e to the negative s. And then we are done.